thank you all for coming this Wednesday evening, especially given that it's Wednesday and on a Tuesday. So thank you for recognizing that unusual date. There's a few housekeeping things before we get going. First of all, I'll introduce myself. I'm Krishna. I'm co-president of the society with Bram. So this talk is being recorded, first of all, in the manner that was stated on the sign-up form. We ask you to keep your mics off and your cameras off for the talk. If you have any questions, do put them in the chat, and then say if you don't understand something, you can put it in the chat and I'll speak out on your behalf. Otherwise, we'll do a Q&A at the end, where you can have your mic on, the camera on, and all that. All right, so to introduce our speaker, we have Professor Nicola Spaldin all the way from ETH Zurich. She's Professor of Materials Theory there, and she developed the class of materials known as a multiferroics, which I think she'll talk a bit on tonight. This has been a widely acclaimed development for which she received the 2017 L'Oreal UNESCO for Women in Science award. She's also a passionate science educator and has a favorite lecturer at ETH. So I hope you'll join me in welcoming her, and Professor, the floor is yours. Thank you.
Okay, thanks a lot, Krishna, and thank you all for coming. It's great to be here, even if only virtually. So before I start my presentation, while I can still at least see the chat, I want to ask you all a question, and maybe you could type your answers into the chat for everyone to see. So I want you to think about what you associate with the term civilization. So I'll give you a minute. There's a chat with everyone button, and I think you should all be able to, correct me if I'm wrong, Krishna, but I think you should all be able to type into the chat what you think about when you hear the term civilization.
Yep, straight in the chat. You can should be available for everyone.
Cities, yeah, that's a good one. Technology, art, culture, laws, culture, society, culture. Culture is coming up a lot. Yeah, I guess we're all becoming uncivilized right now because we can have no culture because it's all stopped writing. Human society, interrelations, human. Okay, very good. I'm going to try and start my presentation while you're all thinking. Connection between people, I like that one. Okay, if this doesn't look like an opening slide, then somebody shout up and tell me, because all I can see now is my slides. I don't see anything else, so you'll have to speak up if you don't see that. Okay, so I think many of you came up with the things I thought about, kind of museums, history, world-class universities, don't forget that one, theater, music, and concerts and so on. Maybe somebody mentioned that since then, really leading systems of government, maybe you would associate with civilization. But I want to make the case tonight that actually civilization is just a measure of the state of development in material science. And I have data here or evidence for that here, because from the Stone Age to the Bronze Age to the Iron Age, every major development in human civilization was marked by, or even you could say it was driven by, advance in material science and engineering. So for example, the transition from hunting and gathering to permanent settlements in agriculture was facilitated by the use of stone tools. Urban centers evolved when when metal processing became available, and then countries and empires and literature really took the development of iron and so on. So yeah, human civilization then is really just a measure of progress in material science. And that continues today when we live in the Silicon Age. So we name our eras of human development after materials even. And today, of course, as you all know, silicon is the material that underlies the technologies that enable much of our modern way of life. So all microelectronics and information technologies are based on silicon. And over the last decades, the last 50 years or so, since the first silicon-based transistors, we've really improved the properties of silicon-based microelectronics to an astonishing extent. And we've grown very used to the idea that all the time our devices will be smaller and faster and cheaper and have greater capability. And so I have a nice example, which I think many of you won't remember, such a clunky old computer with almost no memory or capability compared with today's smartphones, which are much smaller and of course have much more functionality. And as you all know, this progress in device physics is described by Moore's law, that the exponential increase in capability of silicon-based microelectronic devices. And we've really got quite, I'd say, comfortable or really used to the idea that this kind of progress will always continue. But of course, it won't, or maybe it won't, and it certainly won't continue with silicon-based microelectronics, at least in its current kind of paradigm, because we really start to run into fundamental physical limitations as we start to reach, devices start to really reach the size of a silicon atom. And so this kind of steady progress that we've become quite complacent about, I'd say, will have to end, and we won't be able to rely indefinitely on smaller, faster, cheaper, lighter devices with more and more functionality. Now, sometimes it's, you know, one might think that doesn't really matter. I mean, certainly my smartphone, if it gets any smaller, I can't see it without my reading glasses, and I don't feel like I need any more functionality in my microelectronics, even when I have to do all my teaching from home by Zoom and so on. But it actually really does pose a problem for human society. And that's because our microelectronic devices use really a lot of energy. So this is a projection, or well, it's from 2019 on, it's a projection. It's a plot of the annual energy consumption used by information technologies in terawatt hours from 2000, and as I said, the last 10 years or so is a projection, and the earlier years are data, and the projection is with more widespread use of information technologies in the Western world, and as emerging regions start to expand their use of information technologies, if there's no change in the way that we do our information processing and storage, if we don't have any new device paradigms, then by some projections, by 2030, information technologies will be using about 50% of the world's energy. And this is really a lot. It's obviously not a sustainable pathway. And notice that this is not just because of the end of Moore's law. Even before the end of Moore's law already, this line is going up extremely steeply. And so we have to obviously change. We have to come up with some kind of new device paradigm, and maybe an acceptable level for information technologies would be to be using only about 10% of the world's energy. And so to do this, we have to move beyond the silicon age, and we have to come up with a new way of doing microelectronics, of doing information processing, of information technologies. And to do that, we need a new material. So I don't know how many material scientists we have in the audience, but myself and you guys, we get to do this for our job. We get to design these new materials that will enable the new eras of human civilization. Okay, so I thought I'd tell you a story, since I know mostly you're students in the audience, of how, of kind of my personal story of how I came into new materials design. And I'm telling you this story a little bit to illustrate that you know, science doesn't go in a kind of linear fashion. So this is really that there's quite a lot of luck involved, and circumstance, and asking the right questions in the right place at the right time is probably at least 50% of what's necessary in order to, or the key to kind of making progress. So about 20 years ago, a little bit more, I was a postdoctoral researcher, and I was interested in the properties of certain ferromagnetic materials. So these are materials that have magnetic dipoles, north and south poles, and they can be addressed, they can be tuned or modified using magnetic fields. And I was working, or I chose to work in a group. My postdoctoral mentor's group was an expert in what are called ferroelectric materials. These may be a little less familiar to some of you. They're materials with positive and negative electric charges, so electric dipoles, and these can be tuned or addressed with electric fields. And our plan had been to take some of the tools and techniques that my host group had developed for studying, actually computationally and theoretically studying ferroelectric materials, and applying them to the study of ferromagnetic materials. And actually the name ferromagnet comes from the fact that most magnets are made of iron. The name ferroelectric, most ferroelectrics don't have iron in them. The ferro just illustrates the fact, or describes the fact, that the phenomenology of the two kinds of materials are very similar. So that was the plan, but in the course of this development, or developing these methods, I noticed, it was not really rocket science, that the kinds of materials I was working on, typical ferromagnetic materials, materials like iron, they tend to be kind of black metals, whereas typical ferroelectric materials, this is an example of barium titanate, it's a oxide-based ceramic, they're very different. They tend to be transparent, they tend to be ceramics. And there were no materials that we knew of that fell into both classes. We couldn't find any materials that at the same time were ferroelectric, that had these electric dipoles, and were ferromagnetic, that had magnetic dipoles. So this seemed a bit strange, and so I went home one weekend. This was before the days of efficient internet searching. I went home with it's actually a 6-volume, I think, if I remember rightly, handbook on ferromagnetic materials, and the one book that existed at the time on ferroelectric materials. And I kind of looked through both of these, looking for materials that were in both. And I couldn't find any. And this struck me as the question that then, were there really no magnetic ferroelectrics? And if not, why not? Seemed to me to be just the most captivating question. And finding its answer, I would say, became something of a, I'd like to say passion, maybe an obsession. So this is a little picture. So then I moved a year later to take up my faculty position at UC Santa Barbara. This is a picture of the campus, and basically restructured my research plans around answering this question of why there were so few magnetic ferroelectrics, and if it was true, why was it true, and then how could one make a magnetic ferroelectric? And I think we were able to answer this question not because we were smart, not because I was the first person to ask it. It had been asked many times before, actually largely in the former Soviet Union, but because I kind of came to it at the right time, in that the tools of theoretical physics and of computational materials had reached a stage where it was just a small step really to be able to find the answer. So we did, some kind of working out some basic physics and some playing around with computer programs, and after a few years, we're actually able to answer the question, why are there so few magnetic ferroelectrics? And it turns out to be really, really simple. So when I started exploring this question, I thought there may be some profound symmetry reason or some basic law of physics or some that said these two phenomena couldn't coexist at a kind of a Landau theory level or something. It turned out it's really, really simple, that the chemistries of the kinds of atoms that make good magnets, so if you think of your typical ferromagnets, iron, cobalt, and nickel, are kind of these guys in the middle of the transition metal block, are just different chemistries from the elements, the atoms, that are good at making electric dipoles in solids. So there was really nothing, I'd say, profound at a physics level. It's basically that just the two chemistries associated with the phenomena are different. And for the experts, I don't know how many of you are kind of in the materials chemistry area, but those of you who are will recognize that in order to be magnetic, one needs to have partially filled orbitals that should have rather localized electrons to give them local magnetic moments. And this tends to happen from partially filled 3D orbitals in the middle of the transition metal series. To be a ferroelectric, then you have to have your anions off, or your cations, your positively charged ions in a solid, so represented, for example, by this black circle here, they have to move away from the center of any anions, represented by the red atoms here. If they stay in the middle, this guy on the left doesn't have any electric dipole because the positive cation is exactly equal between the negative anions. And to move off center, once it moves off center, it makes an electric dipole. And this chemistry is favored by having empty d orbitals. Basically, if the d orbitals are empty, then they're better able to accept electron density from the negatively charged anion and form a stable chemical interaction. This, for the experts, is called the second order Jahn-Teller effect. And so, of course, if you need to have partially filled d orbitals to be magnetic and empty d orbitals to be ferroelectric, then you have this chemical contraindication between the two phenomena. But importantly, there's no fundamental reason why these two phenomena can't or shouldn't coexist. And so based on that, not intuition, because it wasn't intuitive at the start, but that kind of new intuition that we developed, we thought, okay, then it should be possible to make materials by some kind of trickery that really combine ferromagnetism and ferroelectricity. They're ferromagnetic and ferroelectric. And we started calling these multiferroics. Okay, and so I don't know if there are any questions. Maybe if things are not clear, type them into the chat, and then Krishna can read them out, because I can't see any of you. So I don't know if people are thinking, wait, there's something's crazy, and you're really stuck. Just please let me know. I'm happy to stop and answer questions at any time, or we save them till the end. Okay, so I'm going to show you a couple of ways that we were able to make multiferroics, and the first one is kind of obvious. If there's some atoms in the middle of the periodic table that are good at being magnets, and atoms in different places that are good at being ferroelectric, then why not just make a material that combines these different chemistries? And so the first example that I'm going to talk about, one of my favorite multiferroics, is bismuth iron oxide, bismuth ferrite. For the experts, it has the perovskite structure. The iron ion is magnetic. It has very large magnetic moment, 5 Bohr magnetons. It's coordinated octahedrally by oxygens. And at the corners of the unit cell here are bismuth ions. And the bismuth ions give the electric dipole because they have a stereochemically active lone pair. And bismuth ferrite actually already existed. It had been worked on already in the 1980s. And again, we were successful with bismuth ferrite, not because we had a better idea than people who tried it before, but because we had better samples. And so because of modern techniques, modern thin film growth techniques, turns out bismuth ferrite is not so easy to make in a good quality sample. But this is a high-resolution transmission electron micrograph from the group of Ramesh. The microscopy was done by Marta Rossel. And you see that, so the white dots here are the bismuth atoms. The very pale gray dots in the center are the iron atoms. You don't see the oxygens in this, this kind of image. But you can see that this film is essentially perfect. And so with this astonishing, I'd say, ability over the last couple of decades to make really, really high quality oxide films, we were able to achieve this multiferroic behavior in bismuth ferrite. And I'll come back in a little while later to look at some of the properties. Another approach that we took to making multiferroics was by basically using very unusual crystal structures. And the example material that I'll discuss in a bit more detail, in which we use this angle, is called etrium manganite. Just looking at the chemical formula, you might expect its structure to be very similar to bismuth ferrite. It has these 2 cations and then 3 oxygens, but it has this rather unusual, and I should point out, none of the ions here tend to be ferroelectric. So this is not a conventional ferroelectric, but it has this unusual crystal structure in which it has planes of triangular yttrium ions separating planes of corner-shared manganese-oxygen trigonal bipyramids. And this is such a weird crystal structure that basically, as you lower the temperature, it kind of collapses. And when it collapses, it makes an electric dipole. So I've tried to sketch here by these little arrows that this building block of the structure kind of collapses. And when it does that, it introduces an electric dipole. And again, we were able to study and investigate the rather unusual multiferroic properties of yttrium manganite because we had, because of modern synthesis and crystal growth techniques. So I have to show you this picture because I'm trained as an electronic structure theorist. And when I moved to the ETH, I set up an oxide single crystal growth lab. So I'm extremely proud of this. I'm very excited. This is our furnace. This is a video of a crystal of yttrium manganite growing in the furnace. So the furnace basically has mirrors that concentrate a light beam and make the sample extremely hot. And we slowly pull the sample through this floating zone, this molten zone where it's melted by the heat from the light beam, and it crystallizes into this beautiful single crystal on the other side of the very hot zone. So the crystals can be quite, crystals can be quite large, so we can study them with neutrons. And this one was grown by my senior scientist, Frank Lichtenberg. So again, this kind of convergence of theoretical methods and understanding and modern growth techniques, and also some characterization I'll show you later, really all came together, I'd say, at the kind of end of last century, start of this century, to really allow us to make progress in this exciting field of multiferroics. Okay, but then why are multiferroics interesting particularly? We talked about how we need new materials for new information technologies, but why would it be even vaguely interesting to have something that's both magnetic and ferroelectric particularly? So first, let's talk about why magnetic materials are important. And so the one area in information technologies and in microelectronics where magnetic materials is used is in data storage. And so in that sense, they're very complementary to the kind of silicon-based components of devices, where silicon is doing the processing of the information. Magnetic materials are used for storing it. And they store the data in the orientation of these magnetic dipoles. So for example, south up, north down, compared with north up to south down might be a 0, whereas north up, south down to north up, south down might be a 1, and so on. And these magnetic data bits, magnetic materials are very good at storing data, because these data bits can be very small. they tend to be very stable, and they can be written straightforwardly, and they can be readily detected, because you know that outside of a magnetic material you have a fringing magnetic field that one can detect. So here's an example. This is now rather old-fashioned hard drive, but these stripes here are illustrating opposite orientations of this magnetic dipole sticking out of the plane of the hard disk, and these would represent ones and zeros of digital electrons. But there is a downside with technologies that are based on magnetism, and that's that in order to write or to control magnetic data bits, one conventionally uses a magnetic field. The magnetic field is what's called the conjugate field to the ferromagnetic dipole, and so it's the property that one uses. It's the handle that one uses to control the property. And magnetic fields, in order to make a magnetic field, we need to take a wire and run a current through it. Often one will make a coil of wire. And so this ends up in being a rather large component, and the fact that we're running a current through it means that it heats up. And so this is not a particularly desirable technology to have if you want to miniaturize and use less energy. And remember, our goal here when we said we're really motivated moving beyond silicon microelectronics was to reduce energy use. But in a multiferroic, then one has at the same time both the magnetic dipole and the electric dipole. And our hope then is that we can exploit all the advantages of the magnetic dipole, its stability, and that it can be very small and stable, but then control it via its electric dipole using an electric field. And compared with a magnetic field, an electric field can be made of a very small component. One just needs two little electrodes, and it uses really vanishingly small amount of energy compared with a magnetic field. So we could have our storage. I'm sorry, this may be give you a headache, but storage so that we store within the magnetic dipole, but read it, and write it using an electric field would be the goal. Okay, so then this is the question: can we control the magnetism by electric fields? I showed you already that we can make these materials that have magnetic dipoles and electric dipoles, but so far I haven't shown you any evidence that we can control magnetism by electric fields. So I'm going to show you the very first experiments that we did. Again, this is in collaboration with the group of Ramesh at UC Berkeley, where we were able to control the magnetism with electric fields. And I kind of chose these measurements. They were kind of messy, but because it was really the very first time that this was done, and so it was really very, I'd say it was very exciting. So this is a measurement of the top surface of a thin film of bismuth ferrite, the first of the two multiferroics that we looked at the start. And the picture is taken with a technique called piezo force microscopy, which measures the opposite orientations of the ferroelectric dipole, the so-called domains of ferroelectricity. And so the white regions correspond to the electric dipole pointing, say, out of the page, and the brown regions to the electric dipole pointing into the page, or the other way around. It doesn't matter which, but they're opposite. And this is a picture of just the as-grown sample. So nothing's been done to it. There's been no electric field applied. It's just how it kind of came out of the growth chamber. Now, in the bottom half of the picture this is the same region of space, but it's an image taken using a technique called photoemission electron microscopy, or PEM. And this technique is sensitive to the magnetic domains. And so the first thing I want you all to notice is that the pattern up here of the electric dipoles is very similar to the pattern down here of the magnetic dipoles. So there's this kind of, let's say, this tuning fork. Somebody shout up if you can't see my mouse, because I'm pointing here. If you can't see it, then it probably makes no sense. But there's this kind of tuning fork shape in the magnetic domains. We see it up here in the electric domains. This kind of band here in the electric domains, which is down here in the magnetic domains, and so on. So we see that there's clearly a correlation between the electric and the magnetic domains. Now let's see what happens when we apply an electric field. So now we're applying an electric field. We know that the electric field will change the orientation of the electric dipoles, and we see that it does. As we've gone from the left to the right picture, our pattern of domains has changed. It still looks like a bit of a mess, and now we can do much better at having kind of controlled structures here. But this was, as I say, the very first demonstration. Now let's see what happens to the magnetic domains when we've applied the electric field to bismuth ferrite. So we're not directly, we don't have a handle which should directly work on the magnetic domains. All we're doing is applying an electric field to them, and here's what we get. So the first thing you see is that it's changed. So the electric field has certainly modified the magnetic domains, and the most exciting thing is that it's changed in the same way as the electric dipoles. The magnetic dipoles have followed the electric dipoles. So for example, this dagger kind of shape here is also there in the magnetic domains. If we zoom in on one specific area, say here, that goes from white to brown, we see in the magnetic picture it goes from dark to light. So we really have electric field control of the magnetism. So this was super exciting. I remember at the time I was on sabbatical in Ramesh's lab in Berkeley, and we were there on a weekend measuring this and getting very, very excited. It was, I think, a little oversold, I'd say. It was listed in Science magazine as one of the breakthroughs of the year, along with the Large Hadron Collider. And excited as I am about multiferroics, I do think the discovery of the Higgs boson was perhaps a little bit more significant. But yeah, physicists use electric fields to manipulate magnetic domains in the multiferroic, and success could pave the way for chips that combine the logic functions normally handled by semiconductors with memory functions carried out by magnetic materials, as we discussed already. So this was 2007. So this was almost 10 years after we started thinking about, could a multiferroic be made at all? So to give you kind of an idea of the timescale of these kinds of developments, from like pre-fundamental physics to first kind of materials demonstrations, the first prototype devices were announced, I'd say 2.5 years ago now, by Intel. So about 10 years later then to really a working device. It's a little bit, so Intel published their device in Nature rather than keeping very quiet about it and patenting it, which probably suggests that at the moment they don't think this is going to really set the future of human civilization, but it's anyway exciting that there's a working device. Okay, so are there any questions before I go on? Has anyone typed anything in the chat? I'm now going to shift gears a little bit and talk about some other materials. No? Okay, so I go on.
There was a question.
Okay.
There was a question in the chat asking to understand your motivation better. I guess at some point it would be interesting to know what you can uniquely do with a multiferroic. I don't know if you want to answer that now or perhaps at the end.
Yeah, so maybe maybe this will answer itself. So I guess the thing that one can uniquely do is change the magnetism with an electric field. This is not unique only to multiferroics. I'd say it's unique to, well, no, it's unique to systems that are have simultaneously some kind of magnetic order and electric dipoles. There's a whole class of related materials called magnetoelectrics, which are not necessarily multiferroic, but in which one can with an electric field modify the magnetism, and they're kind of, I'd say, a related class of materials. So that, I think, is the real core functionality of a multiferroic. Actually, I'm going to go on next and show you some other examples, and maybe this will kind of answer itself over the next 5 or 10 minutes or so. Am I supposed to go for like about 45, 50 minutes or something? I'm not realizing I'm not sure how long I'm supposed to talk.
You have 50 to an hour, however
Okay.
long, really.
Okay, very good. I guess you can leave if you're bored. I won't even notice, so it's all right. You can go and get your dinner or something. Okay. So this picture is again a piezo force microscopy image of the ferroelectric domains in a multiferroic. This is from my ETH colleague Manfred Fiebig. And the black and white regions are again representing opposite orientations of the electric dipole. And I show this first of all because it's just gorgeous. I think it's stunningly beautiful. Also because those of you who looked at ferroelectric domain structures will probably never have seen anything like this unless you've looked at multiferroic yttrium manganite. It's really unusual. It's absolutely not at all what one expects to see for a ferroelectric domain structure. Usually they're kind of stripes or kind of square-shaped things, but this is extremely exotic. And it's unusual. The unusual features are related to the fact that it's multiferroic, or the unusual nature of the ferroelectricity permits it also to be magnetic and to be ferroelectric at the same time. And so I want to show you another, in terms of useful aspects of these multiferroics. This will show us another one. So here's just a extract of that ferroelectric domain structure again. And in this particular orientation, actually the white is representing electric polarization in the up direction, and the black is representing electric polarization in the down direction. I'm going to show you again a high-resolution microscopy image. This is not from my work, from the group of Zhang and co-workers. It's very beautiful. And the pattern, when one has up, down, these are the yttrium ions. This is representing up polarization. And when one has down, up, this is representing down polarization. This is how, in the ferroelectric state, these planes of yttrium ions we looked at earlier kind of buckle and make the dipoles. And so if you remember your basic introductory electrostatics class, this means you have a dipole pointing up in one half and a dipole pointing down in the other half. And this region here is extremely electrostatically unstable. It's like if you try to bring two bar magnets and push the north poles together. You're pushing together the two negative ends of two dipoles, and this would, as it is, if it stayed insulating, it would violate Maxwell's equations. There'd be a divergence in the electrostatic potential. And such a structure, for this reason, doesn't ever happen in a conventional ferroelectric, because a conventional ferroelectric will sort out its dipoles to never allow this. Because of the unusual mechanism in this multiferroic yttrium manganite, these kind of domains get kind of trapped in the structure and they can't get out. So the material's stuck with these kind of head-to-head and tail-to-tail dipoles, which make it very unhappy. The way that it responds to that is by bringing charge in here to screen this diverging electrostatic potential. So in this case, when two negative charges are pointing towards each other, it has to bring in some positive charge to kind of cancel them out. And for the opposite case, so if we went, say, down between the black and the white, then it would have to bring in negative charges. It would have to bring in some electrons to screen the diverging electrostatic potential. And this is what it does. So this is now data in collaboration with a group of Dennis Meyer, who's now in Trondheim, taken using a technique called conductive atomic force microscopy, which lets you see the presence of charge carriers. So it scans the surface again with a tip and measures the conductivity below the tip. And with the white arrows, I've marked the direction of the ferroelectric polarization. So here we have a kind of tail-to-tail wall, so it's negative meeting negative, and here we have a head-to-head wall, so it's positive meeting positive. And the etrium manganite is native p-type, so it has a lot of free positively charged holes drifting around in the material, and these accumulate at the tail-to-tail walls to screen this negatively charged, the negatively charged ends of the dipoles. At the head-to-head walls, where there needs to be negative charge, the conductivity is lower. This dark color means there's less conductivity, and that's because all the holes have gone away and come over here. So the fact that the positive holes deplete from this region means that this screens the diverging electrostatic potential and gives an absence of carriers. And then in this region where the dipoles are parallel to each other, you don't need any extra carriers, and the conductivity is just the same as the background. So again, in what these might be useful for, now we have a channel here. If I go back one slide, you see that this channel is one atomic layer thick. It goes from being up polarization to down polarization, really in one atomic layer. I have an angstrom-wide conducting channel, which I can move around with an electric field. I'm not a device physicist, so I'm not really so sure what that would be useful for, but it strikes me as a kind of useful thing, that maybe if I have something I can move around and have be conducting or not at the angstrom level, then maybe one could make some exciting processing or information storage out of that. Okay, so maybe we were about to enter a multiferroic stage, or maybe not. So in the last couple of minutes, I focused a little bit too much on microelectronics, I think. So I wanted to mention just a couple of other directions in which multiferroics are finding device applications that are totally unrelated to what we had in mind when we started out. Again, to kind of illustrate how science and engineering is a very kind of linear, non-monotonic process sometimes. One doesn't always get where one's headed, but maybe one gets somewhere interesting. So I thought I'd start with clean water. Did I say, I can't remember if I said that. This is the United Nations Sustainable Development Goals, so it's nice if your materials are actually contributing something to solving these. So clean water. So this is work from Salvador Pane, also at the ETH, and I was not involved in this at all, but this is a vial of a nasty organic dye, rhodamin B, I think. I apologize if there are organic chemists in the room. And these are nanoparticles, kind of nanowires of bismuth ferrite, which Salvador put in this jar and filtered them out again. And what he ended up with was water. So the bismuth ferrite is proving to be rather useful for what's called water remediation, for breaking up nasty organic things into small molecules and purifying the water. And just a cartoon of how it works. So this is a nanoparticle of bismuth ferrite, which is both magnetic and ferroelectric. And it tends to attract organic pollutants to the charged ends of organic pollutants towards it. And then it also will dissociate the water into radicals, which then react with the organic pollutants and degrade them into smaller molecules. And this process can be activated using, in this case, a magnetic field. And so we talked already about the advantage of using electric fields for saving energy. The advantages of using a magnetic field is that the magnetic field can be applied remotely, right? One doesn't have to contact a system if one's applying a magnetic field. And so in this case, it's kind of the inverse effect is being exploited, the fact that the magnetic field is changing the electric dipoles in the bismuth ferrite. good health. This is an example which will become more and more relevant as our populations age, and this is bone replacement. So this is a scaffold, in this case, with bismuth ferrite particles embedded in it. And these little green things are bone cells that are growing, and these are representing, they're called osteoclasts, I think. Again, I apologize if there's biomedics in the audience. And again, what's being exploited here, this is in vitro, not in vivo, is the fact that one can apply a magnetic, the magnetic field will shake the bismuth ferrite, and the shaking promotes the growth of the osteoblast. So it's believed, for example, that bone growth is aided. Bone is a piezoelectric, it's like a ferroelectric. It's aided by when we walk, the shock of the walking induces electric dipoles in the bone. And of course, if you're injured, you can't go and walk on your bone, but you can, if you use the bismuth ferrite as a scaffold, you can apply a magnetic field to simulate the process of walking, again using the opposite direction, the magnetic field induced change of the electric dipole. Okay, I think I've been a little bit utilitarian maybe. In the last maybe 5 minutes, I'm going to show you an example of a totally useless use of multiferroics, the most not useful example I could think of. And I go back to this beautiful etrium manganite as the example. Okay, so a quick quiz. One of these pictures is a computer simulation of, let me go back a slide, of these intersection points between the ferroelectric dipoles. So these are on the surface, these are points. In 3 dimensions, they're lines, right? They go back into the surface of the material. And the other one is a computer simulation of the formation of so-called cosmic strings, which are textures that are proposed to have formed out of the primordial vacuum in the early universe. And I want you to think about which is which. You can type into the chat. So type yes if you think the red one is the cosmic strings, and no if you think the black one is the cosmic strings. And Krishna, you can tell me what the votes are coming out.
Lots of no's here.
Lots of no's, okay.
1 yes.
Okay, that's very interesting, because in fact, I can't remember which way around it was. So this one, the one on the left is the simulation of the multiferroic. Here I've put the kind of black and white on the surfaces so you can see. And the one on the right was the early universe simulation. But actually the correct answer was that you can't tell the difference, because both of these computer simulations were simulating mathematically the same thing. And so in the last couple of minutes, I'm going to show you how the fact that the process of forming the electric dipoles in the multiferroic is mathematically described by exactly the same potential as the proposed formation of cosmic strings in the early universe, has allowed us to use our multiferroic to study early universe physics. So the multiferroic and the early universe both underwent a similar, what's called a symmetry lowering phase transition that generated these defect lines. And so a symmetry lowering phase transition would be, for example, water freezing and going to ice. It goes from being high symmetry, where every direction looks the same in the water, to low symmetry in the ice, where it looks different when you look upwards or to the right. Associated with symmetry lowering phase transitions is the formation of defects. And so what one sees this here, this is a bit of a cheating example, these ice plates that are forming on the Stockholm archipelago, one sees that at the intersection between these platelets, one has the system, the ice is not perfect, and there's defects formed in between these different regions of ice formation. So here's a blow up of that, different regions of the ice. may have different orientations of their crystal structure, and at the intersections, you form these defects. The ducks know about this. They know to sit in the middle of the platelets, and they also know, you can see up here, the ducks know that there's functionality associated with the defect. So the defects, I guess all of the little algae or whatever go to the defect, and so they sitting and eating or drinking at the defect. In multiferroic yttrium manganite, these defects they're not kind of two-dimensional like in the case of the ice. They're one-dimensional defects because of the special symmetry associated with the phase transition, going from the structure at high temperature where there are no dipoles to the structure at low temperature where dipoles form. And mathematically, the form of the potential that takes us from this high symmetry to this low symmetry structure is this kind of Mexican hat-like potential. In the early universe, the proposed it was a proposal that as the universe expands, it went from a high symmetry vacuum to a low symmetry vacuum, described by a potential that is very similar to the potential we know exists in yttrium manganite, but it's a very flat base. So it's slightly different. Both of these potentials produce these one-dimensional strings. So of course, it's very hard to study early universe behaviors. To study cosmic string formation, you'd have to replay the Big Bang and measure after 10 to the minus 30 seconds. It wouldn't be so easy. Our most powerful tools that we have on Earth, the largest hadron colliders, are about 10 orders of magnitude too weak to study cosmic string formation. One can observe and try to look for signatures of them. So far, they haven't been seen yet. Or one can simulate, as we just mentioned. But what we've been doing instead is doing cosmic string experiments on our multiferroics. So because we have this kind of this system that mathematically is really just the same as the cosmic strings, we do the experiments on our multiferroic that our cosmology friends would like to do on their material. So do cosmic strings exist? Do they form as we think? How did they evolve, and what are their properties? And so we're able to answer questions, for example, like if the universe expanded at different rates, would we get more or fewer cosmic strings? The way we study that is by cooling our multiferroic at different rates through its phase transition and seeing if we get more or fewer of these intersections between the ferroelectric domains. I haven't cheated here. The scale in all cases is the same. It's a 4 micron scale bar. So one can have an undergraduate intern count the number of intersections in all of these cases and see how they vary as a function of cooling rate. And we do indeed see, if we plot the density of these intersections as a function of cooling rate, the red line is the prediction for cosmic string formation, and the red dots are the other data. So this has been a lot of fun, and back to the experiment that went in the chat, really unuseful. Absolutely no, it's absolutely not going to be setting the direction of the future of human civilization. I'm going to end this, my last slide, with some coverage of our kind of amusing, I'd say, coverage, or very creative journalistic coverage of our kind of tabletop astrophysics experiments, which is in National Geographic Daily News, that said the universe's existence may be explained by our new material, the multiferroic material. I really like the comment down here. A new material could help physicists explain the existence of matter, such as this astronaut seen above the Earth, rather than such as this table that my computer is sitting on. But so of course I show you this a little bit of a joke, but not entirely, because as you know, as scientists, what we do is to try to explain our little corner of the universe. This is our kind of our passion. It's our work, and it's also our kind of motivation for doing our work. And so I hope I've given you some flavor of how much fun we have in our little multiferroic corner of the universe, trying to explain why our materials exist and what we might do with them. And I wish you all every success in your research and your studies in your corner of the scientific universe as well. So thanks very much for listening, and yeah, I'm very happy to take any questions. I guess I try stop sharing the screen so then I can see you. Where have you gone? Okay, here. Stop presenting. Okay, now I see people again. Well, I don't. I see people's names at least.
Yeah, great. Well, thank you so much for that talk. It was really great to hear your journey and kind of how you got to multiferroics, and really that last bombshell about the universe. I think that was
yeah.
that's really cool. Yeah. So if anyone has any questions, feel free to unmute yourself and turn your camera on, and you can blast away.
I won't be offended if you want to go and have a beer either.
Maybe a question?
Yeah, sure. Go ahead.
Thank you for the talk. It was very interesting.
You're welcome.
Could you maybe project a little bit into the future about some of the challenges of multiferroics, or some applications that are maybe, I don't know, what we study, or you mentioned the Intel example, but something that's close to, yeah.
Yeah, so because I didn't tell you the whole story with bismuth ferrite, and bismuth ferrite is actually, it's a very good ferroelectric, but it's an anti-ferromagnet. So it has magnetic moments, but they anti-align and they cancel out. So I'd say what doesn't exist yet from just a basic materials point of view is a material that's a good ferroelectric, so it's a strong electric dipole, a good ferromagnet with a large magnetic moment that are coupled and at room temperature. So this, from just a materials design point of view, is a super interesting open question, I think. From a device point of view, they have very clear specifications. So that, of course, because the bismuth ferrite is an anti-ferromagnet, the device ends up being kind of complicated. It then has to be coupled to a ferromagnet. And the way that this device works, it kind of has this multiferroic component, and this talks to a kind of spintronic component, which is electric current based. And this is then able to interact kind of with the outside world. Eventually, you need to get into the electric current. And from what I understand is that the problems are, one would like to be able to switch the ferroelectric with a much lower field than is possible at the moment. And this then exert a larger magnetic field on the next component of the device. So the magnitude of the external field that needed to control compared with the amount of change in magnetism you get out, these are both, the external field's too big and the amount you get out is too small. And they have very well-defined kind of numbers, and they're about an order of magnitude less than what's possible at the moment for the device to be commercially or considered competitive. This is very far from my expertise, though. So we like to do my expertise is much more the basic physics side. Yeah, thanks for the question.
I have a question which might be related to that one, which is, what is it like to work with these materials? Are they a nightmare, or do they require extremes of temperature or pressure, or are they friendlier?
So, I mean, they're oxides, so they're friendly in the sense that, if there's a fire in the lab, I'd rather be there than in the arsenide lab, right? So, so they're certainly environmentally benign. It's very difficult to make intrinsically low defect oxides. And the reason for that is, or transition metal oxides, the transition metals that block along the middle of the periodic table, they're very flexible in their valence states. And so, iron can be 2+, 3+, 4+ quite happily. And so getting the stoichiometry, even the thermodynamic equilibrium concentration, for example, of oxygen vacancies even in a perfect sample is already quite high because the formation energy is so low. So from that perspective, I'm not sure that it'll certainly never be possible to achieve the kinds of purity that one has, for example, in silicon. This is just intrinsically not possible. Many of the new materials are first made with thin film methods, where it's, of course, one's always in equilibrium, but it's possible to play tricks with kinetics and so on. And then it can often be a challenge to get large crystals if one would like to study them with neutrons, to really, because of course films are great for devices, but to really understand particularly magnetic ordering, one would like to use neutrons, and then one needs quite a lot of material, and that can be a challenge as well. So I think from a material synthesis point of view, they're quite interesting, interesting materials.
Thank you.
Thank you.
I think there's a question in the chat from Chris Davis, who asks that instead of building computers with on-off switches, would this lead to computers based on multi-state switches achieved by moving the conductive paths around?
Yeah, so I mean, that's a good question. And again, I have to give you the disclaimer, I'm totally not a device physicist, but I mean, the most naive idea would be, okay, you have two directions of the electric polarization and two directions of the magnetism. So you could imagine a kind of four-state system. With the example I showed of this very narrow conducting channels that you can move around with an electric field, there has been some discussion about could those be used for kind of like a neuromorphic computing kind of architecture. I'd say at the moment it's really just at the discussion level, and so maybe, but I don't even really know how one would go forward in that direction. But certainly, it would be very nice if there are some just device physicists who could totally think outside the box and think, okay, what could I do with such a capability, and then maybe we could try to improve the material in that direction. So I'd be happy to hear any ideas for sure.
Okay, another one in the chat from Guillaume, I think. Sorry if I mispronounced that.
Okay, so the question is, could an ideal multiferroic already exist if you looked at the magnetism of the domain walls? Yeah, so this is a very good question. So it's a huge, I think it's perhaps the most interesting new direction in multiferroics at the moment is what are the properties of the domain walls. And in fact, in the example that I showed you of the switching in the bismuth ferrite, there, in fact, the coupling is really coming from the fact that not directly in the walls in that case, but from the domains kind of reorienting themselves. And yeah, so is there an actual, there's some discussion that the domain walls of bismuth ferrite do have a net ferromagnetic moment, but then of course the wall is not ferroelectric anymore, so that one wouldn't really work. But one could maybe look at a kind of anti-ferroelectric, the domain wall in an anti-ferroelectric would then be ferroelectric and maybe also magnetic. Yeah, I think this is a really interesting direction, just in general, the functionality and the properties, independently of whether you could say, okay, that domain wall is really a multiferroic, but that also possibly, for sure.
Okay. Any more in the chat or in person?
Well, thanks a lot for coming, everybody, and yeah, good. As I said, good luck with your studies. I hope things work out for you this term, that you actually get some classes in real life, and you're not just staring at Zoom the whole semester till Christmas and beyond.
Yes. Well, okay. Well, I think this questions are done then. So yeah, thank you, Professor, for being over your evening and sharing your story and the future with us. It was really interesting, and even I could understand it from my non-material background. So it's well pitched as well. Yeah, so thank you again to you and to people who are still here.
Yeah, you're very welcome. And yeah, hopefully I get to Cambridge sometime soon, and maybe I could actually meet you in person and come to one of your events.
No, hopefully soon.
Yeah, good. All right. Have a good night, everybody. Thanks a lot. Bye-bye.